Welcome to AI Frontiers. Today's episode presents a panoramic view of machine learning research through a unique lens, a single day's output from the arXiv preprint server. On December 18, 2025, 116 papers were posted under the machine learning category. This snapshot reveals the field's real-time pulse, capturing urgent priorities from computational efficiency to scientific discovery. This is the engine room of modern AI innovation. This presentation serves as a guided expedition to map the current frontiers. The journey begins with an overview of the field's seismic shift and significance. It then identifies 6 dominant currents shaping research progress. Key breakthrough insights from the day are revealed, followed by an examination of the core methodological tools powering discovery. The tour concludes with deep dives into 3 particularly seminal papers analyzed in detail. Machine learning has evolved from an academic pursuit focused on optimizing algorithms to a foundational technology woven into societal fabric. It now powers language models, diagnostic tools, and smart grids. This meteoric rise has brought new imperatives, a focus on efficiency, robustness, understanding, and integration. The field is in a powerful adolescence, increasingly self-aware and seeking responsible deployment. The goal is moving beyond black boxes to engineered trustworthy, practical systems. The first major theme is the efficiency imperative, focused on making AI affordable and scalable. Research tackles immense memory demands. For instance, the GreedySnake method orchestrates data offloading to solid-state drives with complex scheduling. Right-gated mechanisms manage explosive memory growth during long context inference. Parameter-efficient fine-tuning, or PEFT, is refined across many papers, with techniques like LoRA enabling surgical adaptation of giant models by updating only a tiny fraction of parameters. This work is critical for real-world deployment in settings like hospitals and small labs. Theme 2 positions AI as a new calculus for the natural world. Physics-informed neural networks, known as GNNs, are key workhorses, trained on both data and encoded physical laws. One paper, More Consistent Accuracy PIN, addresses weakness by implementing an alternating training regimen between easy and hard problem regions. Operator learning aims to teach models to act as whole solution operators, mapping initial conditions to future states. This enables neural networks to solve differential equations for fluid flow or material stress, performing simulation at the speed of a neural network forward pass. The third theme addresses the trustworthiness challenge: robustness, reliability, and safety. Work like ADVA Judge Zero demonstrates that even the systems used to evaluate AI models can be fooled by carefully crafted inputs. Research on learning safe autonomous driving policies equips agents with predictive models of future safety violations, integrating safety into the planning process. Calibration, ensuring a model's stated confidence matches its accuracy, is critical for high-stakes decisions in medicine and finance. This represents a shift from treating safety as a constraint to making it an integral part of system design. A key finding from the day's research provides a dual process theory for the mind of large language models. The work by Kim and colleagues demonstrates that in-context learning cleanly decomposes into 2 neurally separable mechanisms. A task schema module recognizes the abstract type of task, while a binding process links specific inputs and outputs in the prompt. Causal intervention experiments showed 100% schema transferability and 62% binding transfer between models. This explains why models can struggle to override strong factual priors, as pre-existing knowledge can hijack the attention mechanism. Another key finding demonstrates that simplicity can trump complexity. The paper by Collins and colleagues on exploiting ID text complementarity in sequential recommendation found that errors from models using item IDs and models using text descriptions were largely non-overlapping. A simple averaging of the 2 models' predictions consistently outperforms sophisticated, intricately designed fusion architectures. The lesson is clear. Sometimes the most advanced solution is to let diverse experts vote, rather than forcing them into a single, complicated fusion. This serves as a paradigm for any problem with complementary data views. The research is powered by established methodological workhorses. Physics-informed neural networks, or PINNs, are neural networks trained on both observed data and the underlying physical laws encoded in their loss function. Operator learning aims to learn entire solution mappings, acting as fast surrogates for traditional simulation. Parameter-efficient fine-tuning, with LoRA as a prominent example, enables surgical adaptation of large models via injected low-rank modules. Graph neural networks provide native AI for relational data like molecules or social networks. Multi-agent reinforcement learning offers a framework for systems of interacting, learning decision-makers. A paper of the day, Task Schema and Binding. A double dissociation study of in-context learning, by Kim and colleagues, masterfully cracks open the black box. Its goal was to move beyond behavioral description to identify fundamental, separable cognitive components. The method employed causal intervention via activation patching across 9 different model architectures. The finding was a clear double dissociation of 2 independent neural processes. This work provides the first causal evidence for a dual process theory of in-context learning, serving as a goldmine for practical prompt engineering and targeted model editing techniques. A seminal paper demonstrates elegant scientific synthesis. Regularized random Fourier features and finite element reconstruction for operator learning, by Yu and colleagues aimed to bridge scalability and robustness in scientific machine learning. Its hybrid method, RRFF-FEM, combines randomized approximations with novel frequency-weighted regularization and a projection onto a classical finite element basis. The finding was remarkable noise robustness coupled with competitive accuracy and lower training time. Its significance lies in showing that smart, principled hybridization of classical and modern methods can outperform brute force neural scaling. Another seminal paper champions the wisdom of simplicity. Exploiting ID text complementarity via ensembling for sequential recommendation, by Collins and colleagues questioned the trend toward complex fusion architectures. The method trained separate state-of-the-art models using only ID embeddings and only text embeddings, followed by a detailed error analysis. The finding was that a simple ensemble of these models consistently outperformed intricate fusion baselines. This work is a vital corrective in an era of increasingly Byzantine models, offering industry practitioners an immediately implementable recipe for a performance boost. The research momentum points toward clear future directions. Unification and principled composition will advance, turning AI development into a more modular engineering discipline. Hybrid modeling will deepen, featuring tight integration of data-driven AI with first-principle simulation. The pursuit of causal understanding and control will intensify, moving from observing correlations to performing targeted interventions on model internals. Finally, continuous adaptation, monitoring, and governance will become paramount as deployment scales, addressing both the technical challenges of lifelong learning and the socio-technical challenges of system oversight. This AI synthesis and review was created through a multi-step process. The narrative content was synthesized using the GPT DeepSeek model, specifically DeepSeek Chat. The text-to-speech synthesis was performed using Google's TTS technology. Image generation and visual design utilized additional Google tools. A human expert review was conducted for accuracy and coherence. It is important to note that while reviewed, some oversights may still exist within the synthesized material. In this podcast, we bring you the latest breakthroughs in computer science and AI, straight from arXiv. From neural networks to quantum computing, we simplify complex research so you can stay ahead. Whether you're a developer, researcher, or tech enthusiast, AI Frontiers keeps you informed daily. Thanks for listening. If you enjoyed this episode, subscribe for daily updates. See you tomorrow with more cutting-edge AI insights. Disclaimer. This video uses arXiv.org content under its API terms of use. AI Frontiers is not affiliated with or endorsed by arXiv.org.